general relativity step by step. We've got this nice equation here, this nice simple equation for Q, and you'll remember that Q equals Q of R. I'll just pinch in a little bit. What was Q? Well, the line element squared that we were considering was minus dt squared, d being all proper, being proper time for all the galaxies, plus a of t squared, which is the Hubble expansion term, times dr squared plus q of r times the angular terms. So that was d theta squared plus sine squared theta d phi squared. Is that right? So q of r equals r, q of r squared, that should be. Tells me we've got flat space. At least we've got Minkowski space. Minkowski space. Okay, well, we better see what our equation gives us. We've got q dash squared, minus q dash dash equals 1. It's not entirely straightforward. It's a little bit of a trick to solve it. What I'm going to do is to write down that p equals dq by dr. And then I'm going to make the observation that q dash dash equals p dash by definition, which is dp by dr, which is dp by dq by dr, which equals p dp dq. Okay, so we've got this nice expression for q dash dash. So q dash dash equals this thing here. So that says that q dash squared minus q times p dp dq equals 1. That's quite nice. So what does that tell us? Well, that tells us that p squared equals 1 plus p times q times dp dq. So just rephrasing this, it says that pq dp by dq, I'm just turning it into a form that I can integrate, p squared minus 1. So that says that dq over q equals, taking this up to the right hand side, equals p dp over p squared minus 1, and I'm going to multiply both sides by 2 because I want the top to be the differential of the bottom. Now, bearing in mind that the integral of dx over x equals log mod x, we can just integrate this directly. So that tells us that the log mod p squared minus 1 equals 2 times the log of q. That's nice, isn't it? Plus a constant, and I'm just going to call it c for the moment. So what does that tell us? That tells us that mod p squared minus 1 equals e to the power c times q squared. So that splits into two cases. We've got p squared minus 1 is positive. We've got p squared minus 1 is negative. And each one of these has got a different solution. Let's do the positive one first. I'm going to write e to the c equals k, and that tells me that p, which is positive, p squared minus 1 equals k q squared, and this says that p squared minus 1 equals, well, it's the other way around, minus k q squared. So we can write these things down in a slightly different way. Remember, originally I defined, where is it, p equals dq by dr. Well, I'm going to back substitute into that now. So that says here that p squared minus 1 equals plus or minus k q squared, which is both of these equations together. So that says that dq by dr equals 1 plus or minus k q squared, and that's squared, and so that tells me that dq by dr equals the square root of 1 plus or minus k q squared, So dq over root 1 plus or minus kq squared equals dr. And we can integrate both sides as we wish. That's nice. Right, well, let's try it. Let's try that. That's the integral of dq over 1 plus or minus kq squared. Right, so I guess this splits. What I can do is I can call k positive or k negative, and because here what we've done is we've got k always being positive because it was e to the power something, but I can exploit this sign ambiguity in terms of k and express that sign ambiguity in the choice of k, capital K, being positive or negative. So what I've got there is that dr equals dq, I guess I could integrate these, over the square root of 1 plus k q squared, where k is either positive or negative, depending upon the sign of p squared minus 1 here. Well, I certainly can't be bothered to do that in my head, so I'm going to use Maxima to do it. dq over 1 plus root kq squared. Go to the keyboard. Integrate. I'm just going to do a simple one just to check that it works. The reason I do that is that I'm never quite sure that q hasn't got some special meaning. It might mean quit or some other kind of peculiar thing. It might be lambda calculus or something. So I'm just checking that integrate works. Integrate. And of course I've forgotten what the thing is. It's root 1 plus k squared. 1 over the square root square root of 1 plus k times q squared, comma q. And straight away it fires back a question. It doesn't give me an answer. This is one thing which I find simultaneously very frustrating and very powerful about Maxima. Mathematica doesn't do this. Mathematica just gives you a general answer, but Maxima, for whatever reason, gives you a question. Is k positive or negative? Well, let's try positive. Positive. There we go. Arc shine root kq over... arc shine... Can I move that over? No. Arc shine root kq. So that says here that... just a minute. That says there that r equals, and of course I can't remember the formula, arc shine root kq over root k. Arc shine root kq, I'll say q times root k. Was that the positive or the negative branch? That was the positive branch. Yes, that's good because we're taking the square root of something positive. Over root k. Plus a constant, I guess. And here r equals, well, let's do the other one. Let's scribble out that answer. Oh no, I've got to do the whole thing again. I can integrate 1 over the square root of 1 plus k times q squared with respect to q. Now it'll ask me again, and I'm going to say negative this time. Somewhat more complicated. Look, it's giving me some help here. Somewhat more complicated. I'm just going to write this on a bit of paper. Minus arc sine, not hyperbolic this time, kq over root minus k over root minus k. Okay, I've just written it down on a bit of paper here, so I'll put it down onto here now. So it's minus arc sine kq over root minus k upon root minus k, plus another constant here, I guess. Okay, so I've got these nice equations here. I guess the first thing to start thinking about is this k term here, but I'm going to require that q of r equals 0 at r equals 0. If you look at the, so that'll pin down k. If you look at the metric, which I've got written down somewhere, here we go. It should be reasonably obvious to you that if you change theta and phi when r equals 0, we can't have any we can't have any change there. So we can just dispense with that straight away. And so that tells us straight away that k equals 0. So I can just forget that. Oh, that's nice, isn't it? Now what I'm going to do is I'm going to write, for these two equations here, I'm going to write that root k equals, which way around will it be? 1 over r0, where r0 equals some length. And of course here I'm going to root minus k equals 1 over r0 again. That just makes my life a lot easier. And so if I've got this k is positive and k is negative, I've got those two solutions there. They will appear, if I invert, I can say that for k is positive, we've got that q equals r0 sine, hyperbolic sine, of r over r0. There we go, just by inverting that and making that substitution. And for k is less than 0, we've got q equals r0 sine r over r0. You see, this way we don't need to worry about complex or imaginary solutions because, well, this is why Maxima asked me if k was positive or negative, so it didn't need to fool around with complex arguments, which is nice. I guess we've got another solution, which is k equals 0. Well, if you just follow through the follow through it, it just works out that q equals r. Is that r0? Yeah, that's right. Q equals r0. So we've got our nice solutions of q. This one corresponds to Minkowski space. These correspond to a non-flat space. And I will talk about the details and the meaning of this in subsequent screencasts. But I'm going to stop there because this has already gone on 12 minutes, far too long. Stop.